The final type of special limit that we're going to look at is not necessarily specifically a limit itself, but it's a theorem. It's called the squeeze theorem. And it helps us solve limits that are unsolvable by any other method. So what am I talking about? We're talking about a function like this, x squared times sine of 1 over x. If we plug in 0, we get 0 times sine of 1 over 0. So we can take the sign of numbers, but we can't take the sign of something that's undefined. So 0 times sine of undefined. We can't do this. We don't have any sort of value that this is. We could say that the limit does not exist, but maybe it does. And so that's what the squeeze theorem helps us answer. Plug in here as well, we get 0 sine 1 over 0. Once again, 0 times, let's just say sine of undefined is undefined. So 0 times undefined is something undefined. The idea of the squeeze theorem is that if we have two functions that we know are always greater and always less than the function that we're interested in. So in this example on the left, x squared, you can see, is always greater than our red function. And negative x squared is always less than our red function. And x squared is always greater than negative x squared. If this is true, then at a point at which the limit is equal for the outside functions, then the limit of the inside function must be the same. So what does this mean? Okay, let's take a look. Let's take a look at the first one. So we know negative x squared is less than or equal to x squared sine 1 over x is less than or equal to x squared. If we take the limit as x goes to 0 of all of these functions, limit as x goes to 0, x squared sine 1 over x less than or equal to the limit as x goes to 0 of x squared. We can solve the outside limits using direct substitution. Plug in, we have 0 less than or equal to this limit is less than or equal to 0. So this limit, because it's greater than or equal to 0 and less than or equal to 0, must be 0. So I'm gonna skip this line and just say the limit as x goes to 0 of x squared sine 1 over x is equal to 0. So this is how we apply the squeeze theorem. Let's look at the next example. We do the same thing. The limit of the left side, the limit as x goes to 0 of negative absolute value of x less than or equal to this limit. I'll write it. Limit as x goes to 0, x sine 1 over x less than or equal to the limit as x goes to 0 of the absolute value of x. Using direct substitution, we find this to be 0, this to be 0, so our limit must be 0. Okay, so those are a couple examples that I came up with for you. I came up with the two functions for you, but maybe on the AP test, you have to do this without knowing the two outside functions, the function that's greater than or the function that's less than. So let's take a look at a problem where we might have to use the squeeze theorem without knowing those. Okay, so the limit as x goes to 0 of x to the 4th cosine of 3 over x. Direct substitution, once again, we'd have 0 times cosine of undefined, so we can't do this. I'll go ahead and show this for the next one as well. 0 cubed sine of undefined, so can't do it. So we can try to use the squeeze theorem. First, what we want to do is take advantage of the trig functions. So we know that cosine is always greater than or equal to -1 and always less than or equal to 1. I can do the same thing here. Say the same thing about sine. It's always greater than or equal to -1. Doesn't matter what's on the inside. It's always less than or equal to 1. And then we can multiply both sides by the function in front of cosine. Negative x to the 4th x to the fourth cosine 3 over x is equal to x to the fourth. Okay, so the question at this point, is negative x to the fourth always less than or equal to x to the fourth? The answer is yes, because if we take any value of x to the fourth power, it will be positive. Negative 2 to the fourth, what is that? 16. It's going to be positive, even if we plug in a negative value. So if we make all those positive values negative, it will definitely be less than or equal to the positive version of that. So we're good. We can go ahead and take the limit as x goes to 0, negative x to the fourth. This is a lot of writing. It's a lot of writing. 3 over x, x goes to 0, x to the fourth. Direct substitution, 0, 0. This limit is greater than or equal to 0 and less than or equal to 0, so this limit is 0. Awesome. Squeeze theorem used. Let's try it again on the next function. At this point, we've already set it up. Sine of negative 1 over x is greater than or equal to negative 1, less than or equal to 1. So we can try to multiply by x cubed, because that's what's in front of the sine term. But we have an issue. If I plug in a negative value into x cubed, negative 1, for example, cubed is negative 1. So this function will be negative, and negative 1 will be positive. So this function will be greater than this function. So what we'll use is the absolute value again. Why do we use the absolute value here and with x, but not with x to the fourth and not with x squared? The reason is x cubed and x are to odd powers. Because they are to odd powers, the end behavior, one side's going to the negative, one's going to the positive. So if we make them the absolute value, we'll be fine. We'll be fine. X cubed, even if we plug in a negative, it will always, the absolute value of x cubed will always be positive. And then when we make it negative, it will be negative. So this function is always less than the absolute value of x cubed. Okay, so we take the limit as x goes to 0, negative x cubed, x goes to 0, x cubed sine of a negative 1 over x less than or equal to the limit as x goes to 0. And I picked everything going to 0. So this is not the most exciting problem, but that's okay. As we plug in 0 on the left, we get 0 is less than or equal to this limit is less than or equal to 0. So once again, we find that this limit is equal to 0. Okay, the last thing that I put here is challenges of the squeeze theorem. I think something that's really challenging about the squeeze theorem is coming up with the functions that bound our function of interest. So it's very hard to come up with what is always above and what is always below our function, and that has the same limit at 0 in our case, but whatever value of x we're looking for. So I think because of that, on the AP test, you're going to be limited in how the squeeze theorem is applied. I don't think you're going to see anything more difficult than what we just saw. I think you will use sine and cosine between negative 1 and 1, and then multiplying by some power of x, or the absolute value if it's an odd power. All right, those are the two most special or confusing limits. I hope this helped, and I'll see you in the next video.